So for the sake of today's trig identity review, give me an example of a way that I can put cosine squared of x and sine squared of x together and get something else. All right, so Amanda says if I add these two together, I get 1, a nice constant, which doesn't depend on x at all, which is great. Right? Anytime we can make a variable dependence go away, it's usually a good thing. What's the name of this identity? Anyone? Yeah, it is. It's Pythagorean identity. Pythagorean identity. And the reason it's called the Pythagorean identity is that using the definitions of sine and cosine that come from the unit circle, let me just so that we have a quick reminder about how this works. If I have a unit circle here in the xy plane, there it is, then I measure an angle from the positive x-axis. If I call this angle, let's call it t, or something like that. Then where do I find cosine of x, or sorry, cosine of t in this picture? Cosine is adjacent over hypotenuse, and if my angle t is right here, then the adjacent side is horizontal or vertical? Horizontal. So the adjacent side divided by the hypotenuse, and what's the hypotenuse in the unit circle? 1, which is why it's so nice to use the unit circle, because we don't have to divide by anything. So that means that cosine, because it's adjacent over hypotenuse, and the hypotenuse is equal to 1 here, that means that the cosine is just the adjacent side in this triangle in the unit circle, which makes the sine what? Makes it the vertical side. So why do we call the identity we just wrote down here the Pythagorean identity?
It makes a right-hand triangle.
Because we have a right triangle, and in a right triangle, the sum of the squares of the lengths of the sides is equal to the square of the length of the hypotenuse. A squared plus b squared is equal to c squared. Where here the role of A is being played by cosine of t, the role of b is being played by sine of t, and the role of c, the hypotenuse, is being played by 1. So that's why we call it the Pythagorean identity. It follows immediately from the definition of cosine and sine in the unit circle, as well as the Pythagorean theorem for right triangles. That, I think, is the most important identity in all of trigonometry. So if you only remember 1 for the rest of your life, that's the one. Of course, I'm going to ask you to remember more than 1, at least for the sake of today, which means for the sake of the rest of the course, because I don't let you forget anything. So this is one way of combining cosine x and cosine squared of x and sine squared of x in an identity to get something else. What's another way?
Tangent?
Well, okay, we could divide them by one another to get a tangent, right? If I took cosine squared of x divided by sine squared of x, I would get something like cotangent squared of x. Wouldn't call that an identity so much as a definition of what cotangent means. But, certainly we could do that. What I'm interested to do here, though, is I want another identity that is going to be nice and friendly to combine with the Pythagorean identity.
Sine squared x equals 1 minus cosine squared x.
Okay, so that would be a rearrangement of the Pythagorean identity. And this is going to be the kind of rearrangement that we're going to like to use today. That if I just, say, subtract the sine squared to the other side, or maybe I subtract the cosine squared to the other side, what the Pythagorean theorem is useful for as a tool is it's a tool that can let us trade sine squareds for cosine squareds, or trade cosine squareds for sine squareds, whichever we like. So in the process of doing a calculus problem, if I ever have sines that I'm like, gee, I wish those sines were cosines instead, if that would help me, I can use the Pythagorean identity to do that. But I claim that's the same identity still.
How about antiderivatives or differentiating? Like tangent is equal to secant squared x.
The derivative of tangent would be
The derivative. And if we did the same for these, maybe we'd get something along those lines.
We could, although I wouldn't call that a trigonometric identity, really, because you learn trig identities in trig, not in calculus, usually. So I don't want to do something calculus-y to these to make an identity out of them. Do something with arithmetic.
Subtraction.
What happens if we subtract cosine squared of x minus sine squared of x?
Negative
That would happen if I put a minus in front of the cosine also.
Okay.
Right? If I flip both terms, then I would get negative 1. But if I just flip the one of them, this is an identity that doesn't get enough press. So let's try and fix its little PR problem here today. It's not as important as a Pythagorean identity, but when their powers combine, it turns out that they can be pretty powerful together. What do you get when you subtract sine squared from cosine squared? Well, you don't get a constant anymore, unfortunately. But it does give us something that no longer has a square in it. Namely, it gives us the cosine of 2x. This is the so-called double angle formula for cosine. Double angle identity. And what's great about it is that it is so similar to cosine squared plus sine squared that I can take these two identities and combine them together to get new identities. So for instance, what do I get if I take these two equations, these two identities that I have written down here, and I add the second one to the first one? Yeah, so on the right-hand side, I'm going to get 1 plus cosine of 2x. What do I get on the left-hand side? Well, these go away, but the cosine squareds don't. They add together. And now if I divide both sides of this identity, this new identity that we've just derived here, if I divide both sides by 2, what I get is an identity that tells me how to take a cosine squared and trade it out for an ordinary cosine, which is great news. Because this is the kind of identity that we're going to need if we're going to find an antiderivative for something like cosine squared of x. Cosine squared of x, it turns out if we try to take its antiderivative by itself, it doesn't work. But with this identity, we have access to a substitution that will work to find the antiderivative of the thing on the right-hand side. So this is what we might call a reduction identity, something that gets rid of a power on either sine or cosine. But before we leave this slide, I have to ask, well, can we mine a little bit more gold out of this pair of identities? So what if instead of adding these equations together, we decide to subtract them? Subtract the second one from the first. So that on the right-hand side now, I'm going to get 1 minus. What do I get on the left-hand side? Well, what canceled? Yeah, exactly. The cosine squareds are gone now. And I have sine squared minus negative sine squared, so I'm going to get 2 sine squared. And now dividing both sides by 2 yet again, I'll end up with an identity that tells me what sine squared is in terms of that same cosine of 2x that we had before. This pair of identities is immensely valuable in what we're about to do, because the name of the game when we integrate powers and products of powers of sines and cosines is that we're going to try as much as we can to reduce the number of powers that we have. Either by making a substitution, a u substitution that works for us immediately, that's going to be the first thing we do, or if we can't make a u substitution that works immediately, we can at least use a reduction formula to reduce the number of powers that we have. And it turns out we can use those reduction formulas whenever we have even number of powers of both cosine and sine. And when we have even number of powers of both cosine and sine, reduction formulas can get us all the way down to one or the other of these, cosine squared or sine squared. And then we can find the antiderivative that we're looking for. So just to set the stage here, let's suppose that the question we're trying to answer is, what is the antiderivative of cosine squared of x? So I'm going to do that on the next slide. Are there any questions about this one before we go on? So let's first think about that. Integral of cosine squared of x with respect to x. One of the ideas, and this is going to be an idea that will work for us sometimes. turns out it's not going to work for us here, but it will work in other problems, is to take this square and try breaking it apart into a product, cosine x times cosine x. You know, this is just crazy enough to work, but it's going to be a bit too, I think it's going to be a bit too much work to actually make this work out the way that we want it to. Because how would you then propose to attack this integral? Well, you know, we have a tool. We have integration by parts. So we could pick one of these cosines to be u and the other one to be v prime. I'm going to go really fast through this because we're not actually going to do it this way long term. But let me just set up a table, and we'll get our derivatives and antiderivatives in here. So if u is cosine of x, then what's the derivative? And the derivative of that? Okay, I'm just going to stop there for a moment. And then for v prime, if v prime is cosine of x, then what's the antiderivative? Sine of x. And the antiderivative of that? Okay. And so to use integration by parts here, notice what's going to happen if I just keep going in this table? It's just going to keep cycling around, right? Cosine minus cosine, sine, cosine minus cosine, etc. So there's never going to be a place when we can stop if we're using the table method. So instead, I'm going to use the method that does the following. Right? So in the table, remember we can stop in the table if we want to and draw a horizontal line, but we have to put an integral sign on it if we do. So if I start out with this first product and then this second product, then my third product I'm going to take across. So I have three terms to write down here. The first being cosine x times cosine x. So try and keep track of all this. Equals cosine x times cosine x, which is going to give us another cosine squared. And then my next term is negative sine of x times negative cosine of x times negative cosine of x. And then my third term is negative cosine times negative cosine, but because those are on the same level of my table, I need an integral sign in front of them. So we'll get that in here in a second. Times negative cosine of x. And then let's get our SIGN signs appropriately written. Plus. And then this horizontal product is going to need an integral sign. So first one positive, second one minus, third one plus integral dx. Okay. Now let me just go back through and clean up those signs a little bit. So here it's just going to be cosine x times cosine x. And here in the second term I have a total of 3 minus signs in them, so I can cancel 2 of them. And end up with minus sine of x times cosine of x. Okay, and then here I also have a pair of minus signs, which we can annihilate. Okay, and after what it looks like 2 integrals by parts, here's what we have. The same thing we started with, which on the one hand seems like a bad thing. But on the other hand, did you watch the video on the antiderivative of e to the x times sine x, or cosine x, or whatever it was from Khan Academy? What happens when this happens? What can we do? We've integrated by parts twice, and we've gotten exactly the same integral we started with.
That's an equal infinity?
Well, I hope not. Cosine squared of x is a nice bounded function between 0 and 1. It should have a nice bounded antiderivative. It's something very similar to a reduction formula. So here's what we can do. Whatever this integral is, it has some value. It's some function of x, right? So whatever function of x it is, let's call it something. If I call it I for integral, then I'm looking at I on both sides of the same equation. So what that means is, let's condense this a little bit. I've found that I is equal to cosine x times cosine x, so cosine squared x, minus sine x times cosine x, plus I. Now I have an equation that tells me what I is in terms of itself. I can solve for I. I is our integral. It's the thing we're interested in getting. Right? So how can I get I by itself in this equation? Oh. I can't, exactly. If I try subtracting I from both sides, I run into trouble. And I get this funny looking equation, 0 is equal to cosine squared of x minus sine of x times cosine of x, and that doesn't make any sense.
Can't you just use one of the identities?
Well, we could, but that's still not going to remedy the fact that we lost our I. Right? I, the integral, is what we were trying to find, but we've lost our grip on it completely here, because when we integrate by parts twice and we come back around into a circle, I is on both sides of the equation with the same coefficient. So integration by parts, even though it kind of looks promising in the beginning, not so much. But your point about using identities is well taken. We should have done that in the first place, instead of integrating by parts. So let's do that. Rewind all the way to the beginning here. And let's apply that identity we had on the previous slide. That's going to unlock the keys to the kingdom here. Cosine squared of x, according to the previous slide. Jumping around here. There we go. Cosine squared of x is a half times the quantity 1 plus cosine of 2x. That we should be able to take an antiderivative of. So let's do that. Oops. So we're just going to replace cosine squared with 1/2 times 1 plus cosine of 2x. And the caution that I always give is when you're doing this replacement, don't forget that you still haven't done any calculus. So don't forget that integral sign. But now the identity has taken care of the square for us and given us something that we can find an antiderivative for. How should I do that?
Take the 1/2 out.
Let's take out the 1/2 so we can put the focus on what's on the inside, which is 1 plus the cosine of 2x. Now, how are we going to find an antiderivative for 1 plus the cosine of 2x? I heard a whisper over there. Something you'd like to share with the rest of the class? Maybe a substitution? So dx is 1/2 du. And so when I make this substitution, I end up with 1 plus the cosine of u du times another factor of 1/2, like this. Now I'll just ship that extra over 2 to the outside also and get 1/4. And now I just have a friendly antiderivative 1 plus cosine of u du. What's the antiderivative of 1 plus cosine of u?
X plus sine.
Careful of that sign there.
Oh, my.
Yeah. U minus sine of u, right? Because our integral is with respect to u. Plus c. And then we'll just substitute what u was back into our answer. 2x. So 1/4 times a quantity, 2x, minus the sine of 2x. Yeah.
Why is it that it's u and not x?
Oops. Hang on. Yeah, so that one is not your fault at all.
Okay.
I will take full responsibility for that copy error. U plus the sine of u.
I got really.
There we go. We can all sleep a little better at night now. By the way, to further reconcile this connection between u's and x's, imagine if I were to multiply out what's in the parentheses down here at the bottom. I would end up with 1/4 times 2x, which would be 1/2 x, plus 1/4 times the sine. of 2x plus c, right? And this 1/2 x right here is what we would have gotten in the very beginning by taking this antiderivative of 1 with respect to x and multiplying it by that 1/2. So if I had just done the antiderivative from the beginning instead of doing a substitution, I would still end up with that same 1/2 x term at the end of the problem. So we get the same answer whether we elect to do a substitution right away or whether we do it kind of, half and half, if you like. But so this is how we can come up with an antiderivative for cosine squared of x using a trigonometric identity.